So welcome to another class, and today we will start explaining some of the basic things which influenced the Branges in his theory, which was more classical stuff, like from the times of Hardy. And so we will study. We go back to some things in the unit disk instead of the up half plane, and we'll explain some things in there, and we will see the connections with the things we did in the up half plane. And then after that, we'll, by the end of the class, we'll define the Hardy spaces, and in the next class, I will be discussing the structure of Hardy spaces and etc. So for this lecture and the next, maybe the other one as well, I don't know. I'll be following this book here. It's a pretty good book, and mostly chapters 1 and 2. Has a nice introduction for Poisson integrals and then Hardy spaces. So, okay, so before we start, I just want to recall some things and then we can state some results. So in some ways, this will give motivation for the definition of the Branges spaces and the stuff we will do later, and also some background. So let's just recall some steps. So suppose I have f, a function which is analytic, and say, and gamma is some simply connected domain. In the complex plane. So meaning that it's analytic, it means that you can differentiate as a C1 function and it satisfies the Cauchy-Riemann equations. Which another way of writing that. So these are the Cauchy-Riemann equations. So if they satisfy that, then you can show that the function is C infinity, and you can actually differentiate into the variable Z, and everything is nice. But another way of so these are the Cauchy-Riemann equations. Oh, Cauchy-Riemann equations. But another way of writing that is ux. Let me write this. Ux equals the derivative of v, and if you differentiate in y, u, then you get minus the derivative in x of v if f equals u plus iv. Okay, so these are the Cauchy-Riemann equations. Okay. In particular, what you can show then is easy to see that u and v are harmonic functions. That is, if I differentiate twice, u, and if I differentiate twice in x, and then add with the derivative, twice the derivative in y, I get 0. And the same for v, okay? So that's the connection between analytic functions and harmonic functions. Whenever you have an analytic function, it means the real part and imaginary part, they are harmonic, and moreover, they are harmonic conjugates. So, and V is called the harmonic conjugate of U. Okay, and conversely, if you just start with the function U, harmonic, you can solve V. And but you just integrate, for instance, you can solve V, you can find V satisfying the Cauchy-Riemann equations. Basically, one thing you can do is just integrate, let's say, the first equation in Y, let's say, and you see that everything is well defined because of the second equation, and because, sorry, you integrate the first equation and you see that because U is harmonic, then it's also satisfy the second equation, etc., and V will be harmonic. In any case, you can find V satisfy the Cauchy-Riemann equations, and then you can define F as U plus IV, and F will be analytic. Okay, so this is just stuff we see, let's say, in an undergrad class in complex analysis. And it's important here that the domain is simply connected, or otherwise these things, if they are disjointed, then if you have a hole, then it could be a problem. In any case, okay, that's it. So now let's talk about functions in the unit disk. So for now on, I would denote D would be the unit disk. I'm following the notation in the book I just showed. And if suppose if F is analytic in the, and say continuous in the closure, then we know that we have the Cauchy formula, at least at the origin. This is more or less what I did in the first class. Okay, but if you just take real parts, that means that U at 0 equals its average okay, because it's average along the unit circle. And then again, you use the Mobius transform, then similar to what I did in the first class, then using a Mobius transform, when, let's say, you use this transform here, you fix a point, then you see that this Mobius transform sends this point Z0 into the origin, and it also preserves the unit circle. So it preserves the boundary of the unit disk. And if I let I theta to be EI phi, which will happen because it preserves the unit circle, then you can do a calculation. And you see that the factor in the change of variables would be, which will be that, it's exactly 1 minus r squared divided by 1 minus 2r cos of theta minus theta 0 plus r squared, which I will call the Poisson kernel P r theta minus theta naught. And this will hold true if I'm say z naught is r e to I theta naught, for instance. Okay, so that's the Poisson kernel, and that's how it comes from. It comes from this when you use this Mobius transform and you differentiate, you use the change of variables factor. In particular, that will show that so u of z naught is just u composed with tau minus 1 at the origin, which we know what the formula is. It's just 1 over 2 pi integral from 0 to pi of u composed with tau minus 1 e to I phi, let's say, d phi. And then if you use the change of variables, that would be exactly 1 over 2 pi, 0 to pi theta, and then PR of theta minus theta naught d theta. Okay. And then we will always write this as, from now on, as well, not, yes, let me write it like this. F convolved with PR at the point theta naught. So let me define some things. So, so for now on, we always write it convolution. So we'll have to define what convolution is. And I will define what F is. So maybe I should say first, where F theta is just U E I theta, and convolution of two functions, let's say F with G, is just the integral from 0 to pi of F theta. Oh, let me say it theta naught, theta naught. So that would be theta naught minus. In this case, doesn't matter the order here because P is even. So, but to be completely rigorous, I should write theta naught theta, d theta here. Okay, and this thing here is just shorthand for this. Okay. So bottom line, if you have a point, so let me write the formula here. Equals F convolve with PR theta naught if Z equals REI theta naught. Let me put something here. It looks nice. So bottom line, whenever you have a harmonic function which continues up to the boundary of the unit disk, you can write it as a convolution against the function of the angle, which is the continuous function, the boundary of the unit disk, which depends on the angle. And you write it as a convolution against the Poisson kernel. Okay, so this is more or less what we saw in the first class. We actually used that in some of the proofs, I guess in the fragment Lindelof principle, we used that as well. without some explanation, but here's the explanation. Whenever you have such a thing, whenever U is a real part of an analytic function, the harmonic, you can write it in this way. So two things to notice. So remark. So the first remark would be that, well, this formula, let me give a name. Let's see. So formula, we give another name. Let me give like formula 1. Sorry, technical problem here. Okay. Okay, let's go back. So formula. So formula I also holds. I mean, suppose I just want to define a function U using this formula. So formula I actually defines a harmonic function. U whenever f belongs to L1 of 0 to pi. And why that is true? Well, simply because, well, a simple bound you can do. So let's see, let me go back here. So that's the Poisson kernel right here. So a simple bound you can do is you bound this by above, let's say by replacing this guy here by 1. So you are reducing the denominator, therefore increasing this fraction. So if you bound this thing by 1, then the denominator will become 1 minus r, everything squared, which you can cancel with s, with part of the numerator, and then you get the PR of theta is less or equal than 1 plus r divided by 1 minus r. Okay, so as long as r is less than 1, which it will be because this representation is only for points inside the, so in the unit disk, the open unit disk. So this is bounded, so I can integrate against any L1 function, great. And a simple computation also shows that PR, let's say of theta, is just the real part of e to I theta. What is this? Minus plus, I always forget, plus z divided by, yes. Wait, what do I mean? I mean what? Oh, what I mean is, I should write in like this, theta minus theta naught r e to I theta, let's put it z naught, where is r e to I theta naught. Okay, in particular in the variable theta naught, which is the variable we are interested here because it's the variable defined in U, P for each theta, fixed theta, is a real part of a analytic function in unit disk in the variable z naught. And therefore is harmonic. So P itself is harmonic in the variable z naught. So PR theta minus theta naught is harmonic in z naught. Okay, and then basically what you're doing here is taking a continuous linear combination, let's say, is an integral you can think of as a continuous linear combination, let's say, of harmonic functions and therefore harmonic, okay? So this formula here defines a harmonic function whenever f is now 1, okay?
One smaller question.
Yep.
Does this f need to be periodic? Or...
So far, no. Yeah. So far, periodicity is only required when you want answer and when you want to deal with continuity. You want to know if your function is continuous up to the boundary. For instance, the function u. Since your function u, the values of the function u and the boundary will coincide with the values of the function f. If you want, at least most everywhere, which we will show in a moment. Then if you want continuity, then f has to be 2 periodic. But so far, no. So far, it's just a function, and you can continue f periodically if you wish.
Okay.
Yeah, but it won't make much sense because it won't be continuous. It could be anything. It's just an L1 function.
Okay, so this means that the u is harmonic, but is only continuous in the inside of the disk, or is it?
Yeah, yes. Harmonic is always continuous because it's C infinity.
Yeah. Okay.
But yeah, in the boundary, it will recover f.
Okay.
Yeah. So whatever smoothness f will have, then you will have at the boundary. Okay, so now we have the first theorem of today, which, since we're not following in this part the Brown's book, we'll use letters. And we already have a theorem A in the first class, so this will be a theorem B. So theorem B, so first statement of theorem B, if f belongs to LP of 0 to pi, and say 1 less or equal than p less than infinity. And then recall that whenever you have a compact interval, LP is contained in L1. So any bounded function in the, so let's say in 0 to pi is also L1. So the LP spaces are nested. So whenever I ask LP for p greater or equal than 1, then this function is also L1. And therefore I can define U like this. Then PR convolved with F, and then you take F and take the P norm, and LPs are 0 to pi, that converges to 0 when R goes back to 1. Okay, so in principle, so 2 things to keep in mind here. Whenever I have a variable z0, then I write it in polar coordinates. And so the function will be this convolution with the PR Poisson kernel evaluated the angle theta naught. Okay, so in principle, if you fix R, then this guy is just a function of the angle. So it makes sense to do this thing. Okay, because I'm just using for fixed R. But if you want to think that geometrically, what this means, so let me draw a picture. So you have here the unit circle. And so you have a function f here. And then what you do is you're extending the function inside to be harmonic. And then you take some R. Say this is R. And you take this, oops, my circle is terrible. Oh, maybe I actually can use this thing to write a perfect circle. Let's try. This should be a perfect circle. Oh, more or less. So now you have your function f. And this is the inside. This is 1. So let's draw another perfect circle. This should be a perfect circle. Yeah, good enough. And then you have an R here. And then what you're doing is it's just taking, so you extend the function inside to be harmonic, and then you look to this function as a function in the angle at the smallest circle here. So then you have two functions of the angle, the function here on the outside and a function on the inside. And what you're doing is that you're comparing the LP norms of both, and you see that the function here is converging to the function on the boundary, not only almost everywhere, but also in the LP norm. This also implies almost everywhere. So there you go. So that's the first one. The second would be, well, what happens in the p equals infinity case? Well, in the p equals infinity case, what happens is that we're not going to have strong convergence because the mass can be moving around. So you're not going to converge in L infinity, but it's going to converge in some weak sense. So suppose you have a measure mu is a finite, yeah, following my notation, should write it like this. It's a finite measure on 0 to pi. So for instance, it could be just given by a bounded weight, so a bounded function, so say f of theta d theta, and f is bounded. So this second part will cover the L infinity case. Then the same way, if we convolve with the measure and see what happens, oops, then this converges to this, what's called the weak star topology. And this is just saying that so let me write it, that the integral of g of theta PR convolution with mu of theta, d theta, 0 to pi, converges to 0 to pi, g of theta, the mu of theta, for every g continuous, 0 to pi. Okay, that's what means weak star topology. So in a weak sense. And then what about pointwise things? So if f belongs to LP of 0 to pi and is continuous, let's say at some angle, let's say theta naught, then so we converge back to it. Okay, and final one is what? Well, if f is continuous in 0 to pi and 2 pi periodic, then PR convolved with f converges back to f uniformly. Okay, so that would be, so you take the difference, take the L infinity norm, then that's converging to 0. Okay. So great. So these are the basic results about the Poisson kernel. Whenever you have a function on the boundary, you can extend harmonically inside, and you have all of these recovering properties. So in this class, I will just prove some things and give an idea for the other things. I don't want to bore you with a bunch of technical proofs. Okay, so so what can we do here to show these things? So usually the procedure is always the same, and if you already watched a lecture about approximations of unity and etc., it's always the same procedure, and this won't be different. So how do we write, let's say, PR convolved with f theta minus some f theta, let's say? Well, so that's going to be what? So before I put the model line, let's write it like, so we know that the first part is just a convolution against the Poisson kernel. So it's just PR of, let's say, phi, and then I integrate with f of theta minus phi. I just moved the theta minus phi from here to that, which I can because I'm extending the function periodically from 0 to pi, of course. So going back to your question, yes, we always think as these functions being periodically, but at least for me, it doesn't make much sense, unless the function is continuous. But anyway. So that's how we write the first part. And then the second part, since I'm integrating phi, and I know that these guys integrate 1, well, we know that this is always 1, okay? Well, simply because 1 is a harmonic function, and therefore, if I convolve with the Poisson kernel, I should recover it. And so I should get exactly this. So that's because, or else you could just do explicit computation. So what you can do here is just do that. Okay, you move to the inside of the integral. And then what we do now is just apply Mykonski inequality. So what we have is just put the moduli here, and then first we apply the triangle inequality before the Mykonski one. The kernel is positive, so it's always nice to have a positive kernel, because you can do this. So now we have, so let's call this guy, let's see, let's call this guy here, eta of, yeah, let's not call this for the moment. Let's just have this. And then if I do P norm, and then here we use Minkowski inequality. Minkowski, I don't know how to say his name properly. Which I'll explain in a moment, but that would be just less. So I'm doing norm P, and then to be completely explicit, I'm doing norm P in the variable theta, okay? And the Mykonski inequality tells you that you can actually move, say, this variable theta, the LP norm to the inside of the integral. Okay. So what is Mykonski inequality? You can Google it. Let me just explain it quickly. Whenever this works in general, whenever you have like two measures, if you're doing like f of x, y, and do, let's say, LP in x, and then LQ let me see, let's say LQ in X and LP in Y. And then if you have that Q is less or equal than P, that is the outside norm is with a larger exponent than the inside norm, then you have that this is less or equal than doing the LP in Y and then LQ in X. So that's Mykonski inequality. And in our case, what we're doing is, let's see what we're doing. In our case, what we're doing is Q equals, so this has to be greater than 1. In our case, we're doing Q equals 1. Okay, so for Q equals 1, we have that an LP norm, let's say in Y, of the integral of f of xy dx is less or equal than the integral of the LP norms. xy LPY dx. So that's exactly what we did here. The LP norm in the theta, which would be the LP norm bounded by the LP norm of this stuff here. There's an integral inside, so I can put the integral in the outside and the LP norm in the inside. Okay. Any questions here in this inequality? If you didn't see this before, then it's okay. Just Google it, or just take my word that it works. Great. So if you do that, then now I can call this guy here. Let's say this guy. I will call, let's say, now it depends only on phi, eta of phi. Okay, so this was if, let's say, p is greater or equal than 1 is less than infinity. Okay, we still have the also the L infinity case. Yes, so if you had the L infinity case, what we could do is just simply, if p was infinity, and that would work when I assume that the f is uniformly continuous. That would be condition 4. Called in condition 4, I want to take the L infinity norm because I'm saying it converges uniformly. So when p equals infinity, I have to assume that f is continuous. Oh, so then I take the this L infinity norm, and then I can just use this inequality here directly. That would be, oops, less or equal than this. And then here we will have the L infinity norm. It's the L infinity in theta. And then the phi, and then analogously, I can define this function here as being eta. Okay. And then in here, I assume, in here, I'm assuming that f is continuous and periodic. Okay, so in both cases, we see that eta is actually continuous, bounded, therefore bounded. Well, I should say continuous at phi equals 0. It is bounded. And eta of 0 is 0. So let's see. Well, so I'm taking the L infinity norm here, and when I put phi equals 0, I definitely will get just a 0 because the function is uniformly continuous. Great. And in here, I'm taking the LP norms, and this requires some work, but it's not that hard. We can show that when I put phi equals 0 here, then this will actually converge to 0. Okay, so now what we have is so what we have in both situations, so let's say for cases 1 and 4, we have to estimate this thing. And show that this converges to 0 as r goes to 1 for some eta satisfying these conditions. Okay. And now is the standard procedure that I said. So what you can do is just you separate this integral. So what happens, we'll draw a picture here. So what happens with this Poisson kernel is that it has a graph, let's say like this. So this is 0, this is 2 pi, and it goes high, and then it stays very low here, and then goes high. It's 2 pi periodic. So this is PR. So it means that PR concentrates at x equals 0, or x equals 0 plus integer multiples of 2 pi, if you want to think of it as periodically, as a 2 pi periodic. Anyway, so I have to remove some neighborhoods of here and here. So that's what I'm going to do. So 0 theta is a plus 2 pi minus delta to 2 pi, and I integrate the stuff in there. Okay, and note also that since I'm extending the functions to be periodic in the LP case, etc., I should add in eta is 2 pi periodic. So it also vanishes at 2 pi, for instance. And then we have another term. And the other term would be what? The other term would be removing these two small intervals and integrating over 0 to pi, removing these two small integrals. But eta is bounded, so let's say bounded by m. So we have a certain constant m. And then we would have just the integral, let's say, in some interval, I don't know, of this. But we know that the integral of that is 1 if it was in the whole thing from 0 to pi. So I could just say, oh, no, that's not what I want to do right now. What I want to do is just to keep it like this. Yes. Okay. So I have these two terms. So this term is where the kernel PR of phi is very small, which is this part here. And that part is where it's big. But we have this eta here, which is small. It's going to 0. Because at 0, it's continuous, and at 0 and 2 pi is 0. So we can further do is we can simply say that this is less or equal than what? So eta, if delta is sufficiently small, say, so eta will be less or equal than, say, epsilon. So this would be less or equal than epsilon if delta is small. And then we have the integral of this guy, but the integral in the whole bit is 1. So the whole thing from 0 to pi, so I could just bound it by epsilon. And now we have the second term, which is just m times something. And for that, I need a bound. And what I will show is that this bound is something like 1 minus r squared divided by 2r, some constant c and delta squared. Okay. And delta is fixed at this moment. So when I take delta, r to 1, this will converge to epsilon when r goes to 1. So then we will conclude that this bit here in moduli, well, this is always positive. So this is always positive because eta is positive. Yeah, so maybe I should say here. So the limit sup of this thing when r goes to 1 will be less or equal than epsilon, but then epsilon could be anything. So then we will finish. So we just need to show the bound that I claimed, and that is a simple computation because this guy is what? 1 minus r squared divided by 1 plus r squared minus 2r cos phi. And then you have to realize that if delta is less or equal than phi less or equal than 2 pi minus delta, then cos cannot be close to 1. So this thing is less or equal than 1 minus some O of delta squared, which let's say some constant times delta squared. Okay, because cos cannot be close to 1. So then this thing is just bounded by, and then you replace this by 1 minus c delta squared, and then you do the calculations. This would be 1 minus r squared plus 2rc delta squared, and I can just throw away that 1 minus r if I want. And then we just have that, which is good because when r goes to 1, this goes to 0. Okay, for every fixed delta. So as long as I'm away from 0 and 2 pi, I can guarantee this thing goes to 0. So what I'm doing here is proving that this thing here is actually going to 0. Okay, and so that would complete the argument. So that would show, so this shows uh, 1 and 4. So let's see what 1 and 4 was again. So 1 was the LP convergence that we just showed, and 4 was the uniformity. And then we'll leave the other ones for you to work it out, okay? It's just some small modification of the arguments. Okay, great. What else? Now we can move to what? Theorem C. Any questions here?
Just one small comment. I
Yep.
think where you said if delta is less or equals to phi is less or equal to 2 pi minus delta,
Yep.
then I think you don't want the absolute value there. You only want that cosinus of phi is less than 1 minus c times delta squared. Because I mean for phi equals to pi, then
Oh yes, so what I really mean, thank you.
but which is fine because yeah, you just want that the denominator isn't 0. Okay, or like this, yeah.
Yes, is greater or equal than some constant delta squared.
Yeah, okay.
Which will mean what? Is that what I want? Now let's see what exactly I want. And then exactly I want is just cos. Yes, as I said, that would mean that 1 minus cos is greater than that. Yeah, that's what I mean, yes. So it's far away from 1, but it could be -1. Yes, that's what I want. Then I can replace by that. Great, thank you. Any other questions, comments? Great. So now we would move to Theorem C, and that's where we get close to define the Hardy spaces, Theorem C. So let U be some function be harmonic. Okay. Then 1 U Z equals R e to R theta. So U is the Poisson extension of some function f for some f in LP of 0 to pi, if and only if, which is, this is short for if and only if, the sup less than 1 of is finite. Okay. So if you think about what we showed is, well, this is actually a necessary condition because we showed before that using Mykonski inequality, that if U is given by this, yes, so imagine like here. So forget this part here and forget this part here. If I just compute the LP norm, which is what we're doing there, in some internal unit disk, inside the unit disk, so internal circle, then this is less or equal than this times the LP norm of that guy, because we won't have that, but that's independent of phi, because we're extending the function to be periodic. So that will be just the LP norm times the integral of the kernel, which is 1. So we end up concluding that PR of F LP is less or equal than F LP. So of course, if I take the sup here, not only the sup would be finite, but it will also be equal to that because we know that it recovers this function at the when R goes to 1. So this thing here is definitely a necessary condition. And the sup will be equal to the LP norm of little f if U would be represented like this. Moreover, if you just consider this quantity here as a function of R, then this quantity here would be increasing because, well, inside a smaller disk, because of the same reasons, basically, inside of the smaller disk, let's see, if you go to a certain disk radius 1 and you go to a certain disk radius R, then you know that when I go inside, let's say, up to this disk of radius R, the circle of radius R, then U is recovering the function here, and we can also apply, basically what you're doing is just blowing up this little circle here to the big circle, reapplying everything and going back. And then you see that this function here is a function of R is actually increasing. Okay, we'll leave that as an exercise. But the bottom line is, if you have this, then we need to have this. This thing is necessary, but it turns out it's also sufficient. Okay. Second, then we have to deal with so we have to say what P is here. And that is P1 less than P less or equal than infinity. Yes, and then for the case P equals 1, we have a difference because it could be a measure. Is that the case? Let me go back. Yeah, that's the infinity case. Let me make sure that I'm doing the right things here. No, that's correct. The P equals 1 is correct. No, this is correct, yes. Let me go back. So, yes, again, for some, and now will be some measure. If and only if, the same thing, but just for the case P equals 1. Yes, I would check on the book to see if that's completely correct. And the third one is what? And the third one is if U is positive, then if and only if, and that's the Poisson representation we showed, but the version on the unit disk. With some measure mu, where C is greater or equal than 0, mu is some positive, non-negative measure and finite. Okay, so let me just check here really quick. Theorem. Yes. That's correct. Yes. That is infinity. Is one. Yes, everything looks okay. Great. So let me show this result. So what I'm saying here before we prove that. So whenever you have LP, it's the convolution. I'm not completely sure about this infinity here. That was my. Let me remove infinity then. Maybe it holds for infinity, but we won't be dealing with that infinity anyway. Let me do it like this. I'm just not completely sure with that. Yes, because in the other case, we had to remove infinity here. Anyway, yes. So let me put it like this. And then for L1, well, for L1, for L1, it could be just a measure, okay? Maybe it's not an L1 function. Maybe this is a singular measure with respect to the arc length measure on the unit disk, on the unit circle, sorry. So, so it's just a measure. Yes, great. And then if you have positivity, you don't need any sort of condition. This is the Poisson representation we proved already, but the version on the unit disk. Okay, proof. Okay, what do we have? Can we prove this thing? Proof is quite simple, actually. Well, so it's necessary. Well, this is trivial. Let's say for 1 and 2, because we know that if I take the norm P here, this is by Mykonski inequality, that is just less or equal to norm P. So there we go. And if you do, and if F is a measure, and then you do norm 1, Again, by the same Mykonski inequality. As I said, it works for any measures. This is less or equal than the whole measure, so it would be so it will be the total variation. So it will be as a defined. Yep. Before, so it's necessary. So this is for 1 and 2. Then what we can do is, well, conversely, so let me write, let's say, ut of z. So once I fix t, let's say t less than 1, and I fix this function. So now this function as a function on unit disk is continuous up to the boundary. So this here, what I'm doing is just a version of the epsilon trick of the previous class. Okay, but now instead of adding stuff, I have to multiply. So multiply by t. So I know that this is this. Let's say theta naught, the theta if z equals r e to I theta naught. That is true. Great. Which you can write as, let's say, u t e I theta naught convolved with pr. Let's say let me put a dot here. Dot pr at the point theta naught. This whole thing at the point theta naught. No page. Yes. Great. So you can do the same thing, but what do you know is you know that the sup, let's say from 0 less than t less than 1 of the LP norm of these functions, LP in theta is finite, okay? And then we use this abstract, as I like to call abstract nonsense kind of stuff. You just use some theorem of function analysis to guarantee you can extract some sequence of functions that converges. And in this case is the Banach. So using the Banach little glue theorem. So what is the theorem? Whenever you have a sequence of functions with bounded LP norm, so uniformly bounded LP norm, so you can subtract a subsequence that converges weakly to a function in LP. So there is some f in LP of 2 pi, and say Tn going to 1, so that u of t I theta converges to f theta in the weak star topology. Means that if I integrate the left-hand side with a continuous function, that it converges. Oh, I should put n here. Oops. Then if I integrate this side against a continuous function, it converges to this side at the integration of the right-hand side against a continuous function. But then you see, well, the Poisson kernel is a continuous function, okay? So I can just take the limit. If I put Tn here and put Tn here and take the limit when Tn goes to 1, and then there we go. So you have that uz equals to f theta pr of theta minus theta naught, theta, and that checks. So that solves 1. Okay, and for 2 is basically the same, except that we have to find a discrete measure. So what we can do, there are 2 ways. You can apply a similar result, which works in measure spaces with weak star convergence, meaning that the dual is compact in the weak topology, the kind of stuff. The dual of the space is compact in the weak topology kind of stuff. Or you can simply reapply the, or let's say redo the proof we did with using Helly's selection principle. So you use the function instead of the measure, you use the primitive as a non-decreasing function, then you use Helly's selection principle, and exactly the way we did it, and then you can find the measure. Okay, that is 2. And 3 is basically doing the exact same proof for the Poisson representation in the upper half plane, except now you're using the Poisson kernel. The trick is exactly the same. Everything is more or less the same. You have to use Helly's selection principle once again in here, and etc. Basically, you want to show that besides the linear factor, you have something like this. Recall that we had to prove that the measure was convergent. That is, in this case, which is a finite measure, so you have to prove something like that. So you have to come up with a bound for something like that, and that bound comes from you being positive, and it just evaluates at a certain point to realize that it's positive. That is uniformly bounded. And the way we did it in the upper half plane was to evaluate it at the point I, and then we figure out that the measure was integrable when you divide it by 1 plus t squared in there. And in here, you just have to verify it's finite. So I will leave the other ones as exercises. Okay, and you have all you need. You have all you need for solving these problems. Okay, so what I want to do now. So what I want to do is to remark how these things are translated to the upper half plane. We already know some of these things already, but there's some other things we don't know. So the usual way, the classical way that we transfer results from the unit disk to the upper half plane, or any like from results in a certain domain from another domain, is just to use complex analysis, to use some kind of conformal mapping. And in this way, the mapping is explicit and trivial. So using the conformal map, which just means it's a bijection. Let's say from the, if you want to think here, it just means a projection. We call this map phi. So it takes a W in the unit disk and maps to a number in the upper half. And you can task through the calculation to see that the map actually works. And phi of the boundary of the disk is actually R plus a point in union a point at infinity. For instance, if W equals -1, then this goes to infinity, for instance. So that's why we have this point at infinity. So he maps the boundary into the real line. Great, that's the stuff we want. So therefore you can write phi of I theta as t for some t real. If theta is not pi, so it's not -1. And then we can compute the change of variables we have to make. Which would be something like that with a Poisson kernel. And then you compute this, and then you get exactly the Poisson kernel on the upper half plane. And let me tell, which I will write as Py of x minus t, and that works if z equals phi of w. And the way I'm writing here, as I'm using notation, this should be what? Or, and this should be, say, theta minus theta naught, then w should be r e to I theta naught. Yes, now it makes sense. Okay, so that's the change of variables one has to do. So basically, if you have an harmonic function in the unit disk, then use the map phi, and then you have a harmonic function in the upper half plane. Okay, and if it's continuous up to the boundary of the unit disk, it means that it's continuous up to the boundary of the real line and at infinity, which means that you can use Poisson representation in the unit disk, and then you apply this change of variables, and that will give you the Poisson representation in the upper half plane. Okay, so then we have the following result. We have, let's say, theorem B prime, which is exactly as theorem B. You just replace in theorem B d by the upper half plane LP of 0 to pi by LP of the real line, and let's say in 4, replace ask f to be bounded and uniformly continuous. Okay, so let's see what are those changes. Let me go to theorem B. Yeah, so what it's saying is that if you have the Poisson kernel and you have a function in LP on the line, and you have the Poisson kernel on the upper half plane, then this thing goes back to the function on the real line. The same stuff here, if you have a measure on the real line, then it only goes back weakly, which we saw by Poisson representation that it would be this thing, because, well, for instance, this function could be an indicator of an interval, and that would be the Poisson representation result we got. What else? And in 4, I'm saying instead of just asking continuous, then you have to ask also bounded and uniformly continuous. So then you have uniform continuity. So basically what we're saying here, we can see somewhat. So if f in LP on the line, then u, let's say u of xy equals f convolved with py at the point x is harmonic, and u of xy goes back in LP, in the LP norm, to f if y goes back to 0, and that's supposed to be 1 less than p less than infinity. And if you have L1, which have a measure, then it only converts weakly. So if p equals 1, then weak star to 0, and etc. And if f is bounded and uniformly continuous, then in L infinity of the line, I should put x here. As y go to 0. Okay, so that would be a theorem B, B prime, let's say. Any questions here? And theorem C prime would be equivalently, but this one I want to write more explicitly. So let U be harmonic in the upper half plane, for instance, and then what we have, then U equals F convolved with some Py. Again, here I have to say, just to stress, this convolution is the convolution of the line, so it's the standard one, we know. For F in LP of the line, if and only if the sup of y greater than 0, let's say, of U x y LP in x is finite. That is for P less than infinity. To U is F convolved with some measure mu, if in a finite measure mu, if and only if the sup in y of the L1 norm is finite. And finally, if U is greater or equal than 0, if and only if, and that we showed already, that's Poisson representation, is Py plus convolution with mu of x and mu finite. When I say mu is a finite measure, what I mean is, oh, finite, in this case it's finite and positive, but when I say finite measure here is with the total variation. Okay. So that would be the analogous theorem C. Any questions here? So this stuff here is the classical Hardy condition for Hardy spaces. So now we can finally define the Hardy space. And I want to define only for, let's see, for 1 less or equal than P less than infinity. If you go in the book, they actually define this for P greater than 0. So P between 0 and 1, which won't be a Banach space, but still will be a well-defined space with a norm, a pseudo norm, let's say, which it won't satisfy the triangle inequality. Anyway, but these spaces will be used in some harmonic analysis for some nice purposes, actually, and it has some nice application. But in this class, we won't use them. Okay, so, but there are Hardy spaces for P greater than 0, and they are of interest. Okay, and what they are, so let me define. So they have two now. So you have the unit disk, and they have the upper half plane, and have this conformal mapping, which you can go back and forth. Some things are easier to prove in the unit disk than the upper half plane, and so on. But anyway, I will define both. So on the unit disk is just functions from the unit disk to C, which your F is analytic. And then you use this condition here to define the norm. And so the norm P, let's say to the power P, let's see, the norm in HP to the power P would be just a sup, I don't need to power P, just a sup of y greater than 0 of the norm of U of f of x plus iy norm LP in x. Okay. If that is finite, so maybe I need some more space. Push this to the side. That is finite. Okay. Oh, that is the upper half plane. Sorry. Let me put the upper half plane here. And then on the unit disk, it's just the analogous one. But then you take the norm of f in HP would be the sup on r less than 1 greater than 0 of what? Of the LP norm of, sorry, f of r e I theta. And then you do no norm p in theta. So that is finite. Okay. So these are the Hardy spaces, and then you see that they have some relation with this harmonic stuff. But basically, these two things here, this thing happens if and only if the real part and the imaginary part satisfy both things. And in particular, if the real part satisfies it, then you know that the real part is given by something like this. So then you can compute the harmonic conjugate, and then you can say that, okay, your function is actually given by some kind of representation, which would be Cauchy representation, Cauchy formula for some function on the, let's say, unit disk, which is, let's say, LP, etc. So we will show in the next class, not in this class, that these are complete spaces, these are norms, and this is very easy to show that they are complete spaces, and these are norms. Then we will show some other properties of functions in these spaces, talk about a little bit about maximal functions and non-tangential limits for functions in the Hardy space of on the upper half plane. And then what else? We will talk about, yeah, Nevalina's class. We already saw what Nevalina's class was in the upper half plane. So now we will see what Nevalina's class is also in the unit disk. And once we all have this, then I will talk about the H2 case, with the Hilbert space case of the unit disk. Oops, of the unit disk. And the H2 case of the, again, in the upper half plane. And then once we have that, then we go back to the Branges book, and we go, we follow the chapters, and whenever and then I will stop at some moments to explain the connections between Hardy spaces and the Branges spaces, and as we go. Okay, so I think that's it for today. Do you have any questions, comments? Okay, great. Thank you.